For example number 3, we have an oil slick that has an area of y is equal to 3 to the 30 times x to the third plus 100x square meters x minutes after a tanker explosion. So this is the area function where x is in minutes. So x is our time variable. Find the average rate of change in the area with respect to time during the periods from, so there's 3 separate parts here. I'll work on part A first. So they want to know what is the average rate of change from 2 to 3. So the picture of that looks something like this. They want to know if I've got a function. I'm just going to again draw an arbitrary function here. Here's time 2, so x equals 2. And then right here is x equals 3. And so they want the average rate of change. So all they want is what is the slope. I always do that at the end there. Let's try it again. Okay, they want the slope of this green line. And that's not too hard to do. So what I need to do is just get the two points here. So this guy right here is given by 2 comma, and then if I plug in 2 into this function, I've got y is equal to 30 times 2 to the third plus 100 times 2. So that's 30 times 8 plus 230. 3 times excuse me, 3 times 8 is 24, so that's 240 plus 200. Okay, so that's going to give me 440. Okay, right there. Now what we're going to do is we're going to get this guy up here. I'll do this guy in yellow. So at time 3, we have y is equal to 30 times 3 to the third plus 100 times 3. So this is y is equal to 810 plus 300. So y is equal to 1110, like that. Okay, and so all I need is the slope of this line. Okay, so what I'm going to do is I'm going to take the change in the y values, 1110 minus 440. I'm going to divide that by the change in the x variable, which is 3 minus 2, which is 1. So let's grab our calculator here. So if we take that minus 440, I get 670 over 1. And so this is 670 square meters per 1 second. Okay? Oh, excuse me, per 1 minute. I'm working in minutes. My mistake. Okay, per minute. So that's where 670 comes from. Now, if you just want to follow the formula, all you got to do is take the function evaluated at your initial point plus the little bits. Okay, so 2 plus 1, which is 3, so f at 3 minus f at 2 all over 3 minus 2, which is essentially what I just did. That this right here is the 1110, and this right here is the 440. Okay, let's look at B. We got to go between 2 and 2.1 seconds. Same deal, it's just that we're taking this point and we're moving it much closer. Now I'm not going to draw it so that they're ridiculously close to one another. I'm just going to draw it out nice. Think about it like we just zoomed in on the function. Okay, so here's x equals 2. Here is x equals 2.1, and so I'll go up. Okay, and I'm going to get the y values for each of those guys. And all I'm really looking for is what is the slope. What is the slope of that guy right here? Okay, so I need the 2 points. So we know that this is at 2, 440, and we got that from right here. Now we don't know what 2.1 is, so we'll do 2.1. We got to plug it into that equation, right? To that initial one. So that's 30 times the quantity of 2.1, 2 raised to the third power. Okay. Okay, I'm going to have to multiply that by 30. And I'm going to add to that 2.1 times, I think it was 100. Okay, so I get 47.83. I just want to go up and make sure that that was my equation. Yeah. Okay, so 47.83. Just like that. Excuse me. So now, if I want the average rate of change, that's the change in the y's over the change in the x's, or the change in the area over the change in the time. So that'll be 487.83 minus 440 over 2.1 minus 2. So this would be 47.83 over 0.1. If we multiply top and bottom by 10, I get 478.3 over 1. So that tells us that our average rate of change is 478.3 square meters, or meters squared, per minute. Now the last part of this problem asks, what's the instantaneous change? Now, one thing I want to point out here is that the slope of this line was more. We had between 2 and 3 seconds, we had 670 square meters per minute that were leaking, or that it was changing at, the oil slick was. Here it's smaller, and that makes sense because the line's going to be less steep. Okay. Now the instantaneous, exactly at 2 seconds. So if someone came in after this explosion, after 2 minutes, if someone came into this explosion at exactly 2 minutes after the explosion occurred, and they said, how fast is the oil slick changing, then this would be the answer. So what we're going to do is we want, when x equals 2, all we want is the tangent line, the slope of the tangent line. Not the whole tangent line, just the slope. And so the slope of the tangent line is given by the change in y over the change in x, dy dx. And so if you remember, y was equal to 30x to the third plus 100x. And so dy dx is going to be equal to 3 times 30, which is 90 x squared plus 100. And specifically, we want dy dx when x is equal to 2. So that's going to be 90 times 2 squared plus 100. So that's 90 times 4 plus 100. So this is 360 plus 100, or 460 meters squared per minute. Okay, and it's that easy to do. Now you notice that this calculation, it's not hard to do. Okay, so if someone came to the oil slick at exactly 2 minutes and they said, how fast is this slick changing? We'd say it's changing at 460 meters squared per minute.